So as Daniel said, I'm Ragnhild Aurlien. I'm also a PhD student at the University of Oslo. So I'm going to take you into the future. So with future experiment LiteBIRD, where I simulate observations and show that we can actually run these through this Bayesian end-to-end analysis as well. So first, just the goals both for LiteBIRD itself and of this work. LiteBIRD is a future experiment that is led by JAXA. It's a satellite that is planned to be launched in the late 2020s to detect the inflationary B modes. So that's inflationary gravitational waves, signals from that. And the main goal of this experiment is to detect the tensor fluctuation in the CMB polarization at a sensitivity of delta R equals 10 to the minus 3. And the goal for this work is to check if we can simulate data for LiteBIRD and run this through Commander 3. And by doing so, also then show that that we can do this when we get the real LiteBIRD data. It's also an important thing to check to do some estimations on the computational powers that we will need to run the full LiteBIRD dataset, as I only simulate a subset of the full mission. So here's just a quick overview of LiteBIRD. I do refer you to Jon Gudmundsson's talk on LiteBIRD tomorrow for more details, but just some quick facts so that you're able to follow this talk as well. So LiteBIRD has 15 frequency bands ranging from 40 to 400 gigahertz and 4,508 polarization sensitive detectors that are divided over 3 halfway plates. That is if you look at the figure, it's on the low frequency telescope, the medium and the high frequency telescopes. Yeah, they are rotating to control both noise and the systematics. LiteBIRD is planning to do observations for 3 years and from the late 2020s. And based on LiteBIRD, I generate my time-ordered simulations with a code called Genesis. This is a code written by Ragnhild. You can find it on GitHub if you're interested. But as soon as LiteBIRD has its own official time-ordered simulations, which will soon be happening, I will change simulation sets and use those instead. But as for now, I use Genesis. It's a Python-based code that simulates time streams for CMB space satellites. So I give it a set of simulated sky maps created by PySM with PySM, and it scans these maps based on the scanning strategy that you can see in this figure. And then it generates the time-ordered data based on that. I'm using an ideal halfway plate in these simulations. That is that I don't just have one pointing angle, one where the telescope is pointing, and combined with the rotation of the halfway plate. It's also possible to inject systematics with Genesis. And the one I include is correlated noise, that is 1/f noise, and see how that works with Commander. I only simulate 1 year of data. This is to keep the full sky coverage, but to then reduce the data volume with 1/3. So I know that LiteBIRD is a way bigger data set, or will be a way bigger data set than LFI. And I know that LFI is approximately 1 terabyte. So when making my simulations, I kind of had that as the upper limit, like 1 terabyte. I knew that our computers would be able to handle that. So then I just even simulated 4 detectors per frequency bands, which gives a total of 88 detectors, since some of the detectors are both on the low and medium frequency telescope, for instance. And to maintain the full mission sensitivity, I scale down the white noise level. So although I have fewer years and fewer detectors, I still have the same sensitivity as the full mission will have. This is important to get the correct component separation results. I use, as I said, PySM maps created by LiteBIRD collaboration. And I have CMB maps with no B modes, R equals 0, and thermal dust and synchrotron foregrounds as with homogeneous spectral indexes. And then I have simulations with just white noise and correlated noise. As this is not meant to be a realistic instrumental model, but more like a toy model to see how this works, I use delta band passes and a Gaussian beam. So what I do in my analysis is that I first take the LiteBIRD specifications, scale it down to 88 detectors. I then generate my time-ordered data simulations with Genesis. I Huffman compress them. And together with my simulated RMS maps with beam files and instrument files, I put it all together into Commander and do the end-to-end Gibbs sampling, as you've heard of already today. I won't go into all the details there. As an output, I get component maps, that is foregrounds maps, for instance, and CMB maps. From the CMB, I then make power spectra and then can estimate R. So now for some data volume numbers. So this is the data volume for the simulations. So with my simulations, I have 88 detectors in 1 year. The total data volume is approximately 200 gigabytes. And after Huffman compression, it's 60 gigabyte. And here you can see on this figure here, you have the temperature as a function of sample number. So this is the time-ordered data for 1 hour for the 40 gigahertz channel. So the red is the noise, and then green is the signal from both the foregrounds and the CMB. And then the noise and the signal together with the blue here. And of course, this is the scaled down noise. So the noise level will be higher for the real data. But you still get a feeling of how this time-ordered data will look like. And then based on these numbers, I do an estimation of how much data we will get from the full data set with 4,500 detectors in 3 years. And I estimate approximately 30 terabytes, which is very close to what LiteBIRD estimate itself. And then I am down to 11 terabytes after Huffman compression, approximately, which isn't that much. It's of course, a lot, but. And then the computational cost, I've been running my analysis on 36 cores. So all these numbers are for that. So for my current sets of simulations, I have a memory usage of 500 gigabytes. And then for the full data set, I estimate that I will need to keep approximately 12 terabytes of memory in in memory while running Commander, since, as you've already heard today, Commander reads in all the data in the beginning and keeps it in memory while running, which makes it way faster, but it also gets a higher memory demand. And regarding time, for one TOD ban, take approximately 80 seconds to do to analyze one ban, and half an hour for all 22 bans. So that gives me, with the component separation, approximately 3 hours for one sample. And that will give me 240 samples in a month, which is quite a lot. It's good. So with the time usage, if I were to still run the full data set on only 36 cores, which I of course wouldn't, I would then have 3 days for one sample, which gives me 8 samples in a month, which is quite good, since if you compare to the 4 samples that, or samples, the 4 iterations that Planck did, this is still better, even though running it on 36 cores would be too little. And even with today, the best computer has 2 terabytes and 128 cores, so more cores at least than what I've been running with. So based on that, we do conclude that it's safe to assume that the memory and computational power that will be available in the 2030s will make end-to-end analysis of the full LiteBIRD dataset possible, especially with increased parallelization of Commander. Now for some results. Here's some plots or some showing LiteBIRD scanning strategy. So here's a resulting frequency map for 1 hour data and 1 frequency. So you can clearly see the scanning strategy of LiteBIRD. And if you add just 1 day, 24 hours of data, same frequency, you get a quite decent sky coverage already. So the bottom here is the RMS map for a whole year of data. And the blue, the lower value, means that this pixel have been hit the more times, and the higher value means that it's been hit the fewer times. So you can see, clearly see this, the scanning strategy of LiteBIRD in this map. Here's some frequency maps. So there's no component separation happening here. It's just after removing 1/f noise. So I have the input is CMB, thermal dust, synchrotron noise, and 1/f noise. And you can see there's some slight changes happening in these GIFs, and that's different iterations of removing 1/f noise. And by then using these maps in the components separation step, you will get several different, like slightly different CMB realizations, which will then show how the 1/f noise has propagated the whole way through the pipeline. And then finally, the resulting CMB map from Commander after component separation. So the advantage of simulating data is that I have the input CMB map to compare with, and it's quite clean, which is it's very good. So it's Stokes Q&U parameter and the unsmoothed and the smoothed version. So to conclude, we have shown that Commander 3 is suitable for analyzing the simulated time order data, and by that also that we will be able to hopefully be able to analyze the real data in 10 years time. And we have also estimated the data volume and the computational power needed. And we do assume that that will be doable in 10 to 13 years. There's a lot of future work happening or to be done. For each new experiment, we do we create a data module in Commander for each experiment. So LiteBIRD has its own spider, has its own WMAP, etc. So I have then created one for LiteBIRD and further development of this with LiteBIRD specific data analysis modules is an important step. Also to increase the complexity of the simulations, to include realistic systematics and see how that propagates with full end-to-end error propagation. Use other sky models and of course further improve parallelization of Commander. And I would like to thank our funders and ask if there's any questions.